Thank you very much. So I will start by introducing a bit what is nonlinear optics. And what kind of experiment. I'm not an experimentalist, so will be a very light touch introduction. Oops. So first, what is meant by nonlinear optics? Let's start by what we have seen on Monday, so by linear optics. So in that case, the induced polarization, when we apply a field, is just depends linearly on the applied field, and the coefficient is the linear susceptibility. So the polarization, we will look at better at this object later on, is defined as the dipole moment per unit volume. So here I just put some simplification just because it's the first slide. So first of all, I just assume that the response is instantaneous. So the polarization at time t depends only at the field applied at times t. I'm also treating P and E as a scalar quantity. Oh, thank you. They don't like the finger. Okay. As a scalar quantities. And then I also assume that the medium is lossless and we have no dispersion. Is this also working? Oh, yes. So now go to nonlinear. So usually we just stop at this, but in reality, the response of a material depends in a nonlinear manner on the strength of the field. And in this talk, I will just restrict to fields that are weak, so I can just carry out this expansion in the power of the field. So you see here that I have that the polarization as this linear term, but that it has a quadratic term, a cubic term, and so on. So I will have a first order polarization, and then a second and a third, and correspondingly, I will have a second order susceptibility and a third order susceptibility, and so on. So, of course, the question is how large are those effects? So let's stay in a non-resonant case. And so this is an argument made, I forgot to put the reference, by Du Bois just at the start, introduce a phenomenological model for nonlinear optics, and it looks at some atom with springs. And then he say that to get the second order polarizability equal to the first order polarizability, one needs in this phenomenological model to get a field, to apply a field which is of the same intensity of the atomic electric field. And that is, well, that's minus 10, no, 10 to the 7, sorry, 10, yeah. It's 10 to the 7 start volt on centimeter. So if you will go to volt on meter, that will be 10 to the 11, I think, of that order. So quite a large field. And if then we go to the expression of the polarization as a power in power of the field, expanded as a power of the applied field, we see that the second order susceptibility as a magnitude which is 1 over this atomic electric field times the first order susceptibility. So the first order susceptibility is of the order of unit. Then this field is 10 to the 7 Stark volt on centimeter. So typically, out of resonance, the second order susceptibility will be 7 order of magnitude smaller than the first order. Then you can repeat the same reasoning for the next order, and you will see that each order will be almost out of resonance 7 order of magnitude smaller. So when we are with weak fields, we have actually very small quantities. So one can say, well, can we really observe this? Yes, in fact, it can be observed with modest field strength. And in fact, the second harmonic generation was first observed in 1961. So just with the first laser that were devised at the time. So that it's something that can be observed quite easily. So now we have seen that how the we have defined those nonlinear susceptibilities, and then we also have seen how large they are. But now we have made some assumption. Yes. Yes. Yeah, that's true. Yeah. Yeah, so what Nicola said that, oops, so if we consider this expression, so of course these are small, but then I have the square of the field. This is smaller, but then I have the cube of the field. And what I measure in the end is the polarization or the current. And that's what makes it possible to have a signal even with such small coefficients. Okay, so I had made some assumption just to not too scary, just to have a first definition, but then just look back at all these assumptions. So one of the simplification I made is that P and E were scalars. Of course, they are vectors. So if we consider the vector nature of the polarization and of the field, then I get, we can just look at, for example, at one component of the polarization, and that can result from the different component of the field. So, for example, in the linear, and then that means that these objects here are not scalar, like in just what I showed before, but they are tensor. And so in the first order, I have a second rank tensor, in the second order, a third rank tensor, and a fourth rank tensor in the third order, and so on. Because you see, for example, in the second order, to get the polarization component I can have a field along just some direction J, and the other component of the field along some direction K, and similarly for a higher order. So those are not just simple numbers, but they are tensors. And so what about this tensor? So of course the structure depends on the crystal symmetry. So depending on the symmetry, you may have that many of those elements may be zero. You may have some, the matrix may be symmetric, or some elements may be equal. So how do you know that? So you can go, for example, to a textbook on nonlinear optics. Here I took this from the Boyd. In the case of second order, you have similar tables for the third order. So in that case, you just look at the symmetry of the crystal system, and then here it just says what elements you are not zero. In the case you may have some relation between elements, and then, for example, you have also the case in which, because there is inversion symmetry, we are in the dipole approximation, all elements vanishes. So you will have in this no dipole-induced second order response, and this is just a case of centrosymmetric system. So this is an example. Then you have, of course, other table for other orders. So also we have considered instantaneous response. So what about non-instantaneous response? So if this is the case, then we'll have that the polarization at time t depends from the field applied at all previous times, and therefore the responses then will just depend on the time of the polarization and the time of the field, and I have to integrate over all time preceding the time I'm looking at the polarization. So here, since I'm in a weak field regime, I still have the just equilibrium. So if you remember on Tuesday morning, so I can still look at differences of times, and so basically these are still one time or two times and three times objects. And then what is usually done is to look at just to go in frequency, so we can Fourier transform and then have just the dependence on the frequency of the applied fields. And to simplify, I can look at monochromatic fields, so that I just have the fields depending on just a single frequency, so I don't need to just sum over all frequencies, possible frequencies of the system, of the field. Okay, so this is just another expression we need. And then also we have considered that the material was lossless and we had no dispersion. So if we introduce losses, these susceptibilities are tensors, are depending on the different times, and they are also complex. So they have a real and an imaginary part. If we introduce dispersion, so I will not touch on this, but then the propagation, we have to take into account the dependence, the space dependence of the susceptibilities, and also we may also look at the propagation of the field in the medium, and there are several phenomena which that I'm not looking at, and I will not look into. So you can look into, for example, the Boyd or other nonlinear textbook. There it's just discussed this point. Okay, so how these nonlinear susceptibilities are measured. Oops. So there is, if you think at the structure of susceptibility of these nonlinear susceptibilities, so they have an order, and then it depends on several frequencies. So this is in frequency space for the input fields. Then, of course, you can see just there is a wealth of possible experiments. You can change, you can look at different orders. You can just change those input frequencies. So, for example, if we look at the second order, this is a small list I took from this other textbook on nonlinear optics. So, for example, you can look at the sum of frequency generation, when this omega 1 and omega 2 are different, and the resulting omega is the sum of the two. Then if these are the same, you will just have second harmonic generation. You can have one of the fields which is a constant field, then you have this Pockels effect, or you can have the case in which you look at the constant field coming out from the process, and this happens, of course, when you have that omega 1 is equal to minus omega 2. So here, just an example on second harmonic generation. So how this is measured can be on transmission of in reflection. This is a reflection, a schematic reflection setup. So one just shines some laser with some intensity I and some frequency omega. Then it just takes the light which is reflected from the sample, and then it filters it. So for example, you can imagine a prism which will just look at, just divide all different harmonics that are present in the incoming light. And then it just look at the intensity of the signal at twice the laser frequency. And so this is what is measured. And then the one has to apply some model to extract the second order susceptibility from there. So this is just to show that this is not something which is directly measured, but there is some model behind, and especially with measurements of 2D materials, there are a few instances in which the experimentalists have used the bulk model to extract the second harmonic generation, from the measurement, and that results in a huge value of the second harmonic generation, which was actually not the actual value, but was due to just using this bulk model rather than this other model, which is more appropriate for having a small thin sample on a substrate. Also, so this is just also relevant for today's tutorial. When we look at the second harmonic generation on 2D, we have to look at what is called the surface. So basically, we have second harmonic second order susceptibility. So basically, we have to integrate over the thickness. So if we say that chi2 is not really depending on the as no dispersion, then we can just multiply this by some thickness, and this thickness, for example, can be the layer separation in the bulk counterpart of our 2D material. Okay, so if we go instead on third order, then, yeah, so, yeah, yeah. Mm-hmm. Yes.
Mm-hmm. On top of which you add the one from the interface. Question is like, is there any rule now to estimate whether one of the intensity should be dominant that can later be decomposed from the experiment? How difficult is to implement both and modeling?
Well, probably if from ab initio is how to take it out, I guess, because if we have an interface. Yeah. So Nicolas, you calculated interfaces, but you look at centrosymmetric. usually, or not? Yeah. Because yeah, yeah.
So the you could consider having a non-sensitive with vast material with the interface, doesn't make it more.
So I propose let's go on with the discussion later. Also because you don't have the microphone and the audience from online. Yeah.
Sorry. Okay, so the same, we can just look at third order. There are several effects. So the corresponding of second harmonic generation is the third harmonic generation. Then we can look at the cases in which we apply constant field or we applied different optical, different applied field with different frequencies. Or we can also look at the same effect, but with the same field. So we measure. So I will just go on the next slide where I looked at this in more detail. So this is the intensity-dependent refractive index. So it's a third order effect. So basically, what I'm measuring is the frequency at the same frequency of the applied field. But so what happens is, so I just put the sample in a focus bin. So the fact is focused, so I have the intensity is changing with the position of the sample. So if I move the sample slightly, I can change the intensity of the field, and then I can just compare the polarization at different position, so meaning at different field intensities. And then I can distinguish I can see that the intensity is changing, and it's changing because of the higher contribution to the polarization, so the third order and the fifth order and so on. And we will see, so this we'll see later, this can be also done by ab initio, and we can extract this information. So now I've just have some overview of what are the interesting the quantities that we want. So we basically would like to compute these nonlinear susceptibilities. So how can we compute those? So we can compute them directly. So you can express them as a sum over states, where so then you can put your the states coming from, I don't know, a density functional calculation. Or if you want to avoid the sum over states, there are some way, like using the Sternheimer equation. Then you can also have something which is more similar to what is in the experiment. So the experiment is measuring the time-dependent polarization. So you can have real-time simulation that measure the compute the time-dependent polarization. And this is what we will see in the following of this talk. So the reason I will explain later what are just the main advantages. Even of course there are also disadvantages with respect to the direct approach. So then we have to say, how do we compute the time-dependent polarization? So the time-dependent polarization is defined as the electric dipole per unit volume. So suppose I have some macroscopic sample there. So here are some possible way one can say, well, so I have to take the electric dipole. So let's say I calculate the electric dipole coming from this sample, just taking the integral over the sample of the position operators times the density. So of course I can compute the density for the sample. Of the other option I may have is, okay, this is a periodic crystal, so I can look at the unit cell and just do the same as here, but just for the unit cell. Or I can just use this relation between the microscopic polarization and the density. So from the density, I can take the microscopic polarization, and then I can perform a macroscopic average. So I don't know if anyone has some experience, but would you pick up one of those in particular? You smell it, you smell it. So those are just all not valid way to calculate the bulk polarization. So in the first case here, if I calculate the polarization for the whole sample, I will also take into account surface contribution, which are very difficult to disentangle. So I will have bulk plus surface contribution, which I don't want. In this case, the polarization that will result will depend on the choice of the unit cell. So you can just think at some very simple 1D case where you can really have the polarization pointing on two different directions depending on how you choose the cell, for example. And in this case, this microscopic polarization that I get from this relation is defined, of course, up to a constant, which will disappear when I take the gradient. So I cannot reconstruct as well the polarization from there. So how is the polarization actually measured? Is actually what is measured is the difference of polarization. So over time, if you apply a field or if you have some material where polarization is comes by applying some pressure, you can measure the current density in the interior of the sample and then just take the spatial average. So you will have this object and then measure the integrate over the time. So you will get the polarization at, so the change in polarization at that time. So inspired by this, the Resta and Wagner built the so-called theory of polarization. I'm not going through all the steps. I'm just giving the final result. So they managed to write the polarization. So this is for ferroelectric. So here the polarization is not time dependent. So I will just go to time dependent in the next slide. So basically they just take the results from a calculation, just a DFT calculation. So these are the periodic part of Consham states that you get, for example, from a DFT calculation. Then they calculate this Berry phase connection. They integrate over the all brilliant zone and the sum over all occupied states. And okay, they take the imaginary part. Of course, you have to use discrete. So you have a discrete K-mesh. So when you discretize, this looks it's quite ugly. looks like this. So where so this just this point kj, and this is the next point. So this is in 1D, just can be generalized in 3D, but the expression are even more ugly. And I think this is clear what are the important ingredients from the 1D case. So as I say, this is actually in is this polarization, but we want the time-dependent polarization. So the in this work by Ivo Sousa and Vanderbilt, this was just generalized to the time-dependent polarization. So the expression you see is the same. Of course, since I'm in potentially in a non-equilibrium, so instead of occupied, I have the filling of the states. And so instead of the block states that come from Kohn-Sham calculation, I will have those block states that are just the solution of this equation of motion. So in this equation of motion, I have an effective Hamiltonian. So I will come back to this in the next slide. And I will have the dipole operator, which is consistent with this definition of the polarization. So if you want to just is the link with the density matrix. So at each time in this state are diagonalizing the density matrix. Of course, I'm assuming no dissipation, no scattering processes. So let's see, I think that's next coming, the effective Hamiltonian. Oops. So here I just exemplify because it's what we have seen very much in the previous days. So we can just use different levels of approximation, and this is one of the nice thing about this method. We can just change the level of approximation by changing this effective Hamiltonian. So we can just plug in the Kohn-Sham results, and then we will just be at the independent particle level. So here I have the second harmonic generation calculated at that level, and here is the linear response calculated at that level. We can just add the change of the R3 potential, so of the mean field potential, when I change the, so sorry, this now is not the density matrix, but the density. And so I'm just introducing crystal local effect. So for this is actually a monolayer of hexagonal boron nitride. So there is no difference virtually in the linear response, while there is a small difference in the second harmonic. And this is just, that was discussed, this sensitivity of to the fields of the second harmonic generation. Then I can apply just quasi-particle correction to this effective Hamiltonian, for example. So here I have the independent particle plus those corrections. And you see that in the case of linear response, I have a simple shift, but this is not true in second harmonic and also higher harmonic, because I have mixing of different poles at different frequency. So that's two photon energy and 1 photon energy in this case. So you see that the shape is quite different. And then I can consider what is the equivalent of the beta-salpeter. So this is the second harmonic generation. In blue is the beta-salpeter-like level, and then compared with what I would get at the first independent particle. So you see actually that there are peaks, excitonic peaks at resonant at 2 photons at 1 photon when you compare with the linear response. So then what are the experiments that we can address? So if we look how the works in just in big blocks, so we have our equation of motion, and then what we input is just the system. So this will be our density functional theory calculation, and the field, the time-dependent field. Then there is the integration of the equation of motion, and then we will get the polarization. And to get the susceptibilities from there, we need to post-processing the signal. So we have seen that by the effective Hamiltonian here, we can determine the level of theory, while we can determine which experiment we want to address by changing the temporal dependency, the dependence, the intensity, and the frequency of the electric field, and then the way we post-processing the output polarization. So some examples. So these are just what we have done, but there are, of course, many other possibilities depending on the experiment one look at. So the simplest one, and you have seen yesterday as well during the tutorial, is the linear response. So you just have a delta kick. This will just excite all the eigenfrequency of the system, and then you can Fourier transform and get the peak, then get the absorption, for example, if you took the imaginary part. If you want some, oh no, sorry, I put second and okay, it should be either nth or second harmonic generation. So any second or third harmonic generation, then we can input a monochromatic field. We solve the equation of motion, and then we can look at a period of our polarization, and then we can sample some points, and then we can expand the polarization. We just take the Fourier expansion at each point, truncated, of course, at some order. And then we can invert that and get the corresponding susceptibilities. And we can also look at third order processes like the intensity dependent refractive index that in the resonant case is also sometimes called the two-photon absorption. If you take the imaginary part of the third order susceptibility. So this is similar. So we just can input a monochromatic field but we vary the field intensity. So then when we look at the post-processing, we will have the polarization. Sorry, this is very small, but we will have the polarization at different intensity, at different field. And then we just expand this polarization as a power of the field, and by just some algebra, by comparing the polarization at field, just say at the field, at half the field and a fourth of the field, we can just extract, for example, the third order susceptibility from there at the frequency of the laser. So this is different from third harmonic generation. So just to conclude and bridge for what we will do this afternoon, what are the important parameters in a real-time simulation? So first of all, and I won't just go more than this line, are all the parameters that are relevant to convergence, to converge the effective Hamiltonian. So if you have the effective Hamiltonian at Hartree plus screen exchange, then you need to have this all the parameters that are relative to that well converged, like you would converge a beta-salpeter calculation. Then more specific on this type of real-time simulation, so the Berry phase polarization and the covariant dipole. So They are just an integration over a k-point mesh or a differentiation, numerical differentiation over k-point mesh. So the k-point mesh is important. So in addition to the k-point mesh that you may need to converge, for example, the exciton, you have also to be careful about the k-point mesh to have an accurate Berry-phase polarization and covariant dipole. And we will see an example. We'll see an example today in the tutorials. And then the integration of the time step for integration of motion, and also the simulation time. So here I have some example. So this is the effect of the k-point mesh. So this is a calculation at a small mesh, 6 by 1. So in blue, you have the calculation done with this covariant. This is linear response. So you can just look at linear response that you get from Yambo in reciprocal space. And then you see a big difference. And these differences are really due to the covariant dipole not being well converged with respect to the k-point mesh. So here you see a larger 48 by 48 by 1, and then you see a perfect agreement between the two approaches, as it should be. So effect of the time step. So if the time step is too small, you can also have, so here, for example, in blue, is a time step which is not small enough with respect to some more accurate time step converged. So you have to be careful about the time step. And also, when you look at monochromatic signal, the simulation time is important. So here, again, you see in blue the one with the too short simulation time, that it's kind of oscillating around the expected results, which is obtained with a larger simulation time. The reason for that is that is the post-processing that is done. So basically, what we are doing, we are just doing our simulation, and when we start the simulation, we always give a small delta kick, and this delta kick will excite all the frequencies of the system, in addition of the frequency of the applied field. So what we are doing, we are just applying some dephasing factor, and we are waiting enough time that those eigenfrequencies, the contribution of these eigenfrequencies is smaller enough so that we can look at the second harmonic or third harmonic signal. And this long enough means that we have to be careful with the simulation time. We have to check that our simulation time is long enough to have a good sample for getting the high harmonic generation. Okay, so this was just the small notes. We will have some experience hands-on today on those parameters as well.
So thank you, Mirta. And if you have any question, yep.
Thank you. Very nice talk. Probably there was a slide where you're showing different theories for second harmonic generations. So my question is that if we are not including the electron hole interaction, let's say in BSC, so can we detect it, the second and third harmonic generation?
So you refer to this?
Yeah.
So this is just the second harmonic generation at a different level. This is the nice of the theory, that you can kind of dissect what is the contribution. So basically, I'll just start from independent particle and then start adding up and see how it changes. So see what is the importance of the contribution, because this is also maybe what an experimentalist will ask, so how large are excitonic effects how important are in this? So of course this is hexagonal bononitride, and it's kind of quite artificial because yeah, the scale is not clear here, but this peak here is will be 3 point something, and so usually the available laser, they will just measure something between 1 and 2. So I think that the measurement we have and we compare in this paper is made here. So you cannot really say about, but for molybdenum disulfide, for example, you can see the you can see just the C excitonic peak, for example. So then you can compare. I don't know if this answers your question.
Yeah, thank you. So there's a more quick question. So you mentioned the delta field for the calculation purpose. Is it specific, or we can use the sinusoidal or Gaussian field also for the perturbing the system?
Sorry?
Yeah, so you mentioned the delta field for the perturbation. So is it specific, or we can choose any other field options like Gaussian or sinusoidal wave?
Oh, okay. So in this one, well, the field is just, yeah, it depends on the experiment you want to carry out. So the monochromatic field is kind of very easy to work with because, as I showed, and all the you have some note? Or?
If you change the field, you would have to deconvolute. Sorry. If you change the field, you would have to deconvolute the effect of the field envelope on the signal you are computing. The delta kick has a big beauty that it doesn't produce any convolution because it's flat in Fourier space. So this is why you tend to avoid this kind of things. I mean, unless you are obliged to do it, it's better to use a delta kick because you don't have a convolution by the envelope of the perturbation.
Yeah. So for example, so if you have a delta kick, then here you will have some delta T1, delta T2, so you can get the susceptibilities at the time, but of course you will sum over all the different order. If you just have any field, for example, with any frequency, then you have to evaluate those integrals. While if you have a monochromatic field, then you have this expression, which is again much easier. So this is why there are those tricky these fields that just make the job easier.
Okay, just last question because we're out of time.
Yeah. Is there any restriction on the number of orders? Can we go up to, I don't know how many orders?
So the restriction is numerical. So this was related to to this. So I should say I went up to the 4th order, and after that the numerical precision of the calculation just kick in, and I couldn't extract anything else. Also, I mean this is of course at perturbation. Of course, if you put a high field, then you are in the extreme nonlinear regime, and then you can see all high harmonic generate. But that's a different story that I think Nicolas will tell. I think, I don't know. So, but if you go perturbatively, then the next order I managed to get it. But yeah, that's it.